Hello everyone, welcome to our presentation. My name is Ibnu Dakikilid. I am PhD student from Okayama University, Japan. On behalf of my supervisor and co-author, I would like to present our paper, Concept Drift Adaptation for Audio Scene Classification using High-Level Feature. First and foremost, I would like to explain our research background. In machine learning, we assume that data that used for model training has similar distribution when the model is applied. However, in real world this condition is different. The data distribution may change because the change of environment, human behavior, and etc. This condition might decrease our model performance over time because the model is trained and evaluated in different distribution. For example, in audio scene classification, we train our model using data that collected during winter. At that time, in the park, we hear people talking, bird sound, and dog bark sound as the event in the park. However, when we evaluate our model using future data in the summer, we will hear new sound, like a wind sound and insect sound. This new sound may affect our model accuracy because in training, the model never hears this sound. To solve this problem, in previous work, we proposed CMGMM or Combined Merged Gaussian Mixer Model to classify scene audio using MFCC or Mel-frequency cepstral coefficient under concept drift problem. In that research, MFCC that contain information of time and frequency in audio scene is used as input vector for CMGMM, and CMGMM can adapt to the concept drift and classify the audio. In this paper, we changed the feature extraction method. We employ a pre-trained audio neural network or PANS to extract the event audio as input vector for CMGMM. PANS event audio vector contain the occurrence probability of the event sound in audio scene. CMGMM is an incremental algorithm that has ability to adapt to the new incoming data. This algorithm has ability to add new component when the new concept identified, and update existing component when the current existing component is changed. This algorithm also has ability to remove component that has low impact to the prediction result as forgetting mechanism. In the beginning, similar to other algorithms, we use training data to train CMGMM and store the base model to use in deployment or evaluation. In the evaluation, we use evaluation data that might have different distribution from training data or data that contain concept drift. When the model detects the concept drift in evaluation data, the model will train a submodel using drifted data. We call this model drifted model. The next step, we copy or combine all components from the drifted model to the current model. In this step, current model will contain all components from the drifted model. Finally, in the last step, we will merge our component in the model by merge similar component and remove the component that has low impact. We select similar component using callback lever divergence and merge the component using moment preserving merge method. So, by using this method, we still can preserve the old concept and adapt to its change and include the new concept. The algorithm advantages are performing adaptation and continuously learning from streaming data with local replacement strategy to preserve previously learned knowledge and avoid catastrophic forgetting. Furthermore, we can use CMGMM in informed or blind adaptation strategy or active and passive. In active CMGMM, we can use a concept drift detector algorithm to detect the concept drift. We can use ADWIN or adaptive windows or KD3, kernel density drift detection. We proposed KD3 in our previous paper. KD3 is a Windows-based concept drift detection algorithm that uses kernel density estimation to estimate the probability density function, then compute the concept drift. The algorithm detects concept drift by comparing the density function of current windows and previous windows. When the difference is larger than threshold, then concept drift is detected. As mentioned before, in this paper, we use PANS as the feature extraction method. To extract the event audio, we use PANS. PANS is a large-scale pre-trained audio neural network for audio tagging. PANS is trained using audio set dataset that contain more than 2 billion YouTube videos from 527 labels. This model based on CNN that consists of several convolutional layers. Each convolutional layer contains several kernels that convolve with the input feature to capture their local pattern. PAN uses log-Mel spectrogram as its input. Log-Mel spectrogram is produced by applying short-time Fourier transformation to the time domain waveform to calculate the spectrogram. Then, Mel-Victor bank is applied to the spectrogram, followed by the logarithmic operation to extract the log-Mel spectrograms. The model that used in this experiment is 14-layer CNN. This model consists of 4 and 6 convolutional layers respectively, inspired by VGG-like CNN. Each convolutional block consists of 2 convolutional layers with kernel size of 3 × 3. Batch normalization is applied between each convolutional layer, and the ReLU nonlinearity is used to speed up and stabilize the training. We apply pooling size of 2 × 2 to each convolutional block for downsampling. Global pooling is applied after the last convolutional layer to summarize the feature maps into a fixed length vector. Maximum were used for global pooling. In this work, we add an extra fully connected layer to the fixed length vector to extract embedding feature, which can further increase the representation ability. Finally, a linear classifier is applied to the embedding feature, followed by a sigmoid operation for tagging tasks. In our case, we will employ the tagging audio as the probability of audio as input vector for KD3 and CMGMM. This graph shows the example output of PANS. Using PANS, we can extract the probability of event sound every frame. To train and evaluate our model, we use 2 datasets, namely TAU and TUT acoustic scene dataset, which contain 15,000 audio segments in 15 scenes. In evaluation, we use 4 type concept drift, namely abrupt concept drift, gradual concept drift, recurring type 1 and type 2 concept drift. In gradual concept drift, it occurs when concept A is suddenly switched by another concept. And in gradual concept drift, it occurs in the future when concept B is appear as new concept and concept A still remain. In recurring concept drift, the old concept might reappear in the future. To overlay the new event audio in scene audio, we use 3 scenarios. In scenario 1, several event sounds that related to the scene were overlaid several times with random timing and gain. For example, a same people swimming sound is overlaid in a beach scene sound. In scenario 2, the event sound were selected from a group of event sound, then overlay with random timing and gain. For example, a car horn sound is randomly selected from several car horn sound. In scenario 3, is similar to scenario 2, but the event sound could be exist in several scenes. To evaluate our model, we use interleaved test then train or frequential evaluation in 2 approaches, active and passive. In active adaptation, we extract the incoming observation using feature extraction method, MFCC or PANS, then do the evaluation. Based on the prediction result, we detect the concept drift using concept drift detector like KD3 and Edwin. When the concept drift detected, we do the adaptation and adapt the model. In passive approach, we do the similar process. However, the difference is the adaptation process occurs in fixed batch data. This table presents the experiment result of CMGMM in active scenario. In average, PEN show better accuracy than MFCC. In detail, MFCC average accuracy is 0.68 and PEN's accuracy is 0.72. In abrupt concept drift, where the concept suddenly changed, the PEN show better accuracy than MFCC in every scenario in abrupt concept drift. There are performance improvements around 3 until 10% when using PEN. Similar to abrupt, in gradual also show similar result. PEN show better accuracy than MFCC in every scenario in gradual. The performance improve around 10 until 11% when using PENs. Recurring concept drift is different from abrupt and gradual concept drift. In this type, all concepts may reappear in the future. The performance of CMGMM in this type is depend on its drift detector. In recurring type 1, PEN show better accuracy than MFCC when using Edwin, and in recurring type 2, PEN show better accuracy than MFCC when using KD3. For CMGMM passive adaptation result, PEN show better accuracy than MFCC when the batch size larger than 50. In small batch size, MFCC show better result. In gradual, PEN show better result in almost all batches except 50. However, the difference in accuracy at 50 was not significant compared to other batches. In recurring type 1 and type 2, PEN show better accuracy than MFCC when the batch size is larger than 100. In small size batch size, MFCC show the better result. Finally, the conclusion of our research, we able to implement the PEN's event audio extractor that has better accuracy than MFCC in both active and passive approach. In active approach, PEN show significant improvement in abrupt and gradual concept drift. In passive approach, PENs tend to have a lower performance in rapid adaptation batches or small adaptation size. Thank you for your time and attention today. We're happy to hear your suggestion, comment, or question, or idea for improvement. See you.